Okay, so good evening. Let's try to continue with the behavioral level modeling, which we have discussed in the last class. I hope you could all listen, hear me. Can someone respond?
Yes, sir, we can hear you.
Yes. Thank you. So the basic idea was, when you go with behavioral level modeling, this modeling style is the one which is quite often being used. For most of the modeling of digital network, this behavioral style modeling is being used. Out of that, this always is used for all design, and initial is used for test bench. And we have also discussed what do you mean by blocking and non-blocking assignment. Blocking means simply giving equal to. Non-blocking, you use the symbol like this. The blocking assignment will make sure that the set of instruction is being executed in serial fashion, whereas non-blocking will make you to execute in parallel. That's the main thing. So yes, inside this always block, we can bring in all the conditional statements like if else, case statement. Now let us see what is this case. It's mere something like you have multiple options. Then you can go with case. Say case, right? Case state, I mentioned here. Now, if I have 4 state, S0, I can keep on describing what is there in state 0. S1, I can keep on describing in S1 what is happening. S2, state S2, what is happening. S3, what is happening. Like this, I can keep on going ahead. And something like what you have in C, you also have while loop, for loop, repeat, for aware, like this, right? So you can also have that. Mainly, it's quite sufficient when you go with these case, if else, and always. Most of the time we use that. So initial and always block, we have discussed what is their difference, how do they differ from each other. So coming down again, yes. Now let's try to understand this one, because this code has something to speak about. Look at here. This is something to speak about a test bench. What is this test bench? Anyway, now let me speak about a little bit of test bench, and then we will see how the coding look like test bench and what are you expected to do in the test bench. So I am making a design. Say let this be, for a simplicity's sake, let me take it as a full ladder. A, B, C, sum, carry, right? So this is my design. Now, we would have seen in the earlier case, we go for testing its functionality by forcing the value for ABC and see what is the value that is we obtain from sum and carry. Instead of doing that, what I can do, I can write a wrapper around this. That is also a Verilog code. Now, instead of forcing the value, I can give the test value which I am intended to test for the design in a program and compile that program and run that program. That program is called as test bench. So what you need to understand is a test bench cannot be synthesized. Cannot be synthesized. What do you mean by that? The test bench will not be converted to appropriate hardware for the design, because its intention is only to test, whereas design code is for coming up with a hardware. So this could be synthesized, whereas this cannot be synthesized. So that's the reason we have some constructs which could be applicable only for the test bench. Fine. Now, next thing. What is expected in a test bench? Or how does the test bench look like? Simple. Say something like this. I have written module full adder with a set of port list like A, B, C, sum, carry. And you have defined everything, it end up with an end module. Okay, that's fine. Now for this, I am supposed to write the test bench. What should I do? Now, it is also a separate Verilog code. So you will be having a module, and module name generally this FA-TB or something like that, test bench. Now the next thing is, you need not have any port list in this. So this port list is empty. You can always define a module with empty port list, because I am going to define the values for that inside my program. So there is no port list in this module for test bench. Got it? So module is a keyword, test bench, FA_TB is the module name. After this, what are you expected to do? Simple. Now, in your design, whatever you would have defined that as wires or input as a wires, those things will be declared as reg here. A, B, C. Or simply, to keep in your mind, all the inputs which has been declared as wire, usually in a design, you always declare the inputs as a wire. For what reason? Then alone any change in the input will immediately get reflected in my design. Otherwise, it takes for the next clock cycle to update. So that's the reason for all input, we make them as a wire. When it comes to test bench, I'm making all the reg, all the wire as a reg, and usually the output of a design will be declared as, these two will be declared as a reg here. Those things need to be declared as a wire. That's it. Wire, sum, carry. So these two are the important changes. You are converting wire to reg to wire. Okay, fine. So now you have defined a module. You have defined which is your reg and which is your wire. Then what next? You need to call your circuit under test or a module under test. Which module are you going to test? So here the module name is full adder. Got it? So bring that full adder module, give the instant name F1, make sure that the port list is same as this order. If not, you can port map by name. Dot A is being connected with A, dot B is being connected with B, like this. Got it? That's all. So that's all. You have defined one module, defined what is reg, what is wire. You have called which circuit or which module to be tested. Now you have invoked everything. What next? You need to feed the value. What is the way to do that? Initial. Use an initial command. Why initial command? The reason for using initial command is anything inside an initial command will get executed only once. So make sure, say something like this. First reset, if at all, if there is any reset, make equal to 0, and any other, whatever you want to make it. After 10 unit of time delay or 5 unit of time delay or 1 unit of time delay, that depends upon your design. You can just go ahead and do that. Then after 10 unit of time delay, make A equal to 0, B equal to 1, C equal to, right? C equal to 1, right? Next, you are given the first set of inputs. After 10 unit of time delay, again assign A equal to 1, B equal to 1, C equal to 1. Then after 10 unit of time delay, assign A equal to 1, B equal to 0, C equal to 1, like this. You can give any number of input test pattern. Once you give it, remember, after finishing all this, you end that module. And anything inside the initial, if more than one statement is there, give it within begin and end. That's all. There ends your test bench, nothing else. So to write a test bench, to watch the signal, you can use $display. $display, A, B, C, colon, the corresponding value of sum and carry, everything you can see, that values can be displayed there. So you can see what is your output waveform. Or you can directly go there. You need not force anything. We will take one example and I will tell you how the test bench is written, and we will also see the output in the test bench. Okay, so basic idea of a test bench is it is just to test the module, not a design module. It is not a design module. What are you expected to do? Right? You are expected to convert wire to reg to wire. The reason is simple. Here you would have given that as a wire that has been fed as from this to this module as a reg module. From here you are supposed to take your output, so this becomes the input for the next stage. Say it becomes reg to wire here. That's it. So convert all reg to wire, wire to reg. Simple. Call the modules circuit under test or module under test. Then you give initial statement. Give all this. One more point. This doesn't involve clock. Now, in case if it is acquiring a clock, say for example, it is a finite state machine, it requires a clock. So how could I do that? When I want to define a clock, then the same clock need to be defined within this module itself. I use always CLK equal to tilt of clock #5. Can someone say this could be begin and end if there is more than one statement? Otherwise, it is a single statement. You need not even have the begin and end. Can someone let me know what will happen if I give always followed by delta 5 clock equal to inversion of clock? This is tilt of clock. In the place of always, if I am using initial, one more initial statement, then what will happen? Can someone let me know quickly? You can give that in the chat box also. What could be the difference? What will I get if I give always? What will I get if I give initial? We need clock cycle repeatedly, so we need to. Very good, very good. Initial exit, yes, simple. That's it. So in case if I am using initial here, the clock will go only like this. Whatever say, let it be 0. If you have initialized the clock 0, then it will go from 0 to 1 only once after a time period of 5 unit of time period. Whereas if I give inside an always block, it's an ever-ending loop, right? So it keep on generating a waveform. After say some 1000 unit of time, finish, you can give $finish. These are compiler statements. So after 1000 unit of time, it will finish the execution of the clock. So that's the way. So nothing else in the test bench. So we have seen what is a test bench, how to write a test bench. Let's get back to this program. So typically this is a test bench. What you could note here, module, stimulus, all the input has been made as a reg. So you are initializing this. Remember all initial block, all always block will get executed in parallel. So initial begin. So I am giving after 5 unit of time A equal to this much, B equal to this much, and end this initial block. Again, one more initial block after 10 unit of time I am giving this value, 25 unit of time I am giving this value, and one more initial block, 50 unit of time I am giving $finish. So make sure you are giving sufficient time for all this interval, then alone the simulation get finished after forcing all the value. Otherwise, if I'm giving this as 10, then immediately after this, in the intermediate calculation of this value, it immediately stops. So that and all you need to take care. So how much time you are giving, what is your clock period, and one more thing, right? Let me do that also, because these are the normal mistake where the designers will do. Let me assume like this. My clock is having 10 unit of time. Okay, means this is the first passage, second passage, it is having 10 unit of time. If I am giving signal, input signal for every 5 unit of time, what would happen? There is a chance, not there is a chance, definitely it will miss the signal or input between two subsequent input. Why it is missing? Because the clock can capture only the signal after every 10 unit of time, but you are changing the input for every 5 unit of time. So if at all, if you want to sample this sampling frequency, this clock frequency should be less. Got it? So under that case, your time interval for changing the input should be 10. Your sampling interval should be 5. Always that sampling interval should be less than that of the time interval under which you are giving your input. This point is very, very, very important. Else you will not get the right answer. So make sure that you are consciously looking this. Right. Coming back, all the other things are fine. Yeah. So this is a simple example. This is for clock generation sector. Look at the code. Module clock generation. First, I am making the clock equal to reg, which is normally input that has been declared as a reg. The point is only this one. I am using 2 blocks or 3 blocks. One initial block, one always block, one more initial block. In the initial block, I am initializing the clock equal to 0. In the always block, for every 10 unit of time, you are going to have a clock pulse. This keeps on generating, but after 1000 unit of time, I am finishing this. So this is a very simple module for generating the clock. Okay, fine. I'm just skipping all this and let's go with some of the. One more important thing. In the assign statement, look at here. We would have used like this, assign y equal to a plus b. There I have said that you need to make sure that the y is always a wire, or you need to declare y as a wire. But when you come inside an always block, the left hand side variable should always be a reg. Why should it be? Why it is supposed to be a reg? So here also you look at this, A and B are my reg. So A and B on my left hand side. Why should I declare that as a reg? The reason is simple. What is that idea? Inside an always block, it get executed only if there is a change in my sensitivity list. So until then, this value need to be stored in this particular left-hand side variable. So to store that value, you need to make sure it is a reg. Say for example, A is having some value after computing this. When the A value can change, till this A value changes and thereby A or B value changes, it start executing and then it get updated. Updated means this value need to be retained till the next clock cycle. When it is expected to retain till the next clock cycle, definitely it need to be a rich. That's the point. So is this important comparison clear? So assign left-hand side variable should be a wire. If it is always, left-hand side variable should be a rich. This is the standing rule while writing a program. Okay, next. Coming on to these two code. Now you could see what is the impact of blocking and non-blocking. Let's take a piece of code, compare these two. Look at this. Now B equal to 0, A equal to 4. I'm just initializing this. So both A and B are registered. It is entering into this always block at A comma B. So since it doesn't involve any passage of the clock or the neckage of the reset, definitely this is going to be what? Combo logic. So begin and end. The reason is I have two statements. If it is only one statement, I would not have used begin and end. So what I'm trying to do, so it adds B plus 2, right? So B is 0 here. So 0 plus 2, 2, that will be assigned to A. So A will be getting the value of 2. After that, look at I am much more concerned about the assignment which is being made. This is a blocking assignment. This is a non-blocking assignment. So once it finished the first line execution, A is going to get a value of 2. The next line is B equal to A into 3. That is 2 into 3. So B will be 2 3s are 6. Okay, fine. Now let's come to this code. Everything remains same except the blocking operator has been changed to non-blocking operator. Now what is going to happen? Let's see. So for this first line and the second line, remember they both are going to get executed at the same time. So what will happen? In the place of B, it is going to take 0. In the place of A, it is going to take 4. So A will be getting a value of 2. B will be getting a value of 12. This is where the difference comes in. This is what I said. So while you make blocking and non-blocking assignment, there could be a change because the way it is getting executed inside an always block. If you have any doubt, you can just put me. I am not able to run model sim. Can someone help me out? Okay. If there is something, then we can do that. Not an issue. Okay. So you can just still be specific. What is that problem? Then probably we can fix that problem. Okay. Then I am just moving all this. Okay. Now let me go on with one more important idea. Maybe some people would be familiar with this. Maybe some people may not be familiar with that. So quickly I will refresh so that will be used for coding, whereby you could easily understand. So that's the reason. Let's do that. Flip-flop and latches, simple. Okay. First, let's make these two clear, and then we will go to flip-flop. What is a flip-flop? Flip-flop is edge sensitive, simple. This is level sensitive. Level sensitive. How can I make flip-flop? Flip-flop can be made by coupling or adding two latches oppositely triggered. Oppositely triggered. Right? So I can get a flip-flop when I attach a positive latch with a negative latch. One will be acting as a master, other one will be acting as a slave. Those theory probably you all have read earlier. The first one is called as a master, second one is called as a slave, because this is going to capture this D input, and after next clock cycle, it is going to give me to the end, which is going to be my output. Or in simple, how do I understand this latch and flip-flop? Simple. I will explain you very simply what is this latch and a flip-flop. Or in functionality wise, how it is going to differ. Let me take this to be the clock. Okay, so this is my clock, and let me take this to be my input. Okay, that's not working. Okay. This is my input. That is data. So if you take flip-flop D, Q, of course Q bar is an inversion, so we don't bother much about that. This is my clock. Got it? Now let's take a flip-flop will have a symbol like this to indicate it is edge triggered. That's the point. Okay, right. Now look at here. Now let me see what is there in Q. Simple. What you need to do is just look at the point where my clock moved from 0 to 1. Time being, I am ignoring the propagation delay. At this point, the value is 0. So simply give your output as 0. How long it will be 0? Till the next rise edge. During that time, the value is 1. Go with 1. How long I should? Till the next rise edge. So these are my rise edge of the clock. Now the value is again 1. Here the value is 0. Now it becomes 0. Now here it is again 1. So it goes on like this. So this is my Q. The inversion of this will be Q bar. If this is a flip-flop, that is positive edge triggered flip-flop. Now the question is next. Or simple, what do you understand? During the rising edge of the clock, D equal to Q. The remaining time period, it's simply retain the last value. That's all. What is D latch? What will be the waveform? Instead of looking the rising edge, you look at the level. During the positive level, come down. Simply copy the whole information to your Q. Got it? How long? Till the next on period comes. During the on period, you get something like this. So again, copy this. Again, move on. Till what? Till next on period comes. In the on period, the value is 1. Then retain the same one. During the next on period, the value is 0. So then go to 0. Retain this 0. Next on period, the value is 1. So go to 1. Sorry, it will not come down. It keeps on retaining. So this will be the D latch output. This will be the D flip-flop output. Any doubt in this understanding? Simple. Latch and a flip-flop. Got it. Next. Let me go with another one more. In the flip-flop, there are two types. Synchronous, asynchronous reset. What do you mean by synchronous reset? What do you mean by asynchronous reset? The point is very simple. Synchronous reset means the reset signal will work only in association with the clock. What do you mean by this? Let me do this. Always at pass edge of the clock. Then if reset equal to 1, out equal to 0. This is how I have written a program. Now what I'm trying to do, my clock is coming like this. This is my pass edge. While my clock is in this interval, I give reset equal to 1. During this point, while my clock is at 0, I am giving reset equal to 1. RST equal to 1. RST equal to 1. Now, If you see your output, the output will not go to 0. When will it go to 0? After this rise edge of the clock, it will go to 0. Or simply, the point is, even if you make reset or if you change the value of the reset, that will get reflected only at the next passage of the clock. It is in synchronous with the clock. Means it goes to the always block, look for a clock passage. If the clock is at passage, then it comes and look for, oh, if reset equal to 1, then make your output. Meanwhile, if you make, after finishing this, if you make reset equal to 0, that will get reflected only during the next time period while it looks the clock passage. That is what you call it as a synchronous reset. So it is like, even if you give reset, that will wait for positive edge of the clock and then respond. What about asynchronous? The same code. I'm just making like this. Always at sensitivity list is passage of the clock or a passage of the reset. You can make it. Then if reset equal to, if you don't mention anything, it means that reset equal to 1, out equal to 0. So what does this mean here? If any of these two changes, then immediately it enters into the always block and start executing. So what does this mean is, even if reset changes, it will immediately go and make your output 0. It will not wait for a clock. That's why it is called as asynchronous reset. That's it. So while writing a program, if at all if you have been asked to come up with D flip-flop with the synchronous reset or asynchronous reset, this is the difference. One more also you will have, in synchronous reset, you can have active high reset, active low reset. Means if I make reset equal to 1, then output goes to 0. Else if I make reset equal to 0, then output goes to 0. So you can have both the way. Synchronous, active high, synchronous, active low. Similarly, in asynchronous also, active high, active low. So like this, you can write a program for D flip-flop. Simple. That's all. We are almost finished. We will take up an example and see how the coding is being done. If you have any doubt, meanwhile, you can put it that in the chat box. Okay. Look at this program. D flip-flop, synchronous active high reset. So what we have done, this is my module name, and I have given the port list. If required, we will put that in the word plus. Word plus, you can. So that it is, or then I need to save this as .v file. Can I save here? I will make D flip-flop .v. There is this node plus plus is good enough. If that is visible, then I need not waste time here. I thought the word size is a little bit small, so you can save this as .v file. Yes, the moment you save, you will get things, keyword get enabled. Okay, look at here. This is the module name, right? So this is my port list. I have clearly defined which is your clock, which is your reset, what is your D input, output is reg Q. Always at positive edge of the clock. By this you come to know that this is synchronous. Begin if reset equal to, why begin? Because you are going having a couple of statements. If reset equal to 1, then make Q equal to 1 tick binary G, or it means that Q equal to 0. That's it. Else D equal to Q or Q equal to D. I mean transferring the value of D to Q. You are ending that and end module. Whenever you use begin, you should always make sure that it ends. Simple. Let's see whether that works. So this is the D flip-flop. Go here, simulate, active reset. So start simulation. Go to D flip-flop. Active high reset. Synchronous, that name should be, there are asynchronous also. I'm just showing only one. Synchronous reset. Go here and make this enable. Once you do that, look at the object window. This object window has all the 4 signal. Select those signal. Now I am not using the test bench. I will show you the test bench in anyone. Right? Selected signals. Sorry. Add to waveform. Selected signal. Okay, I think already one window is there. Oh, okay. It has added twice. So I can simply delete these. Okay, fine. So let me give force a clock. Select the signal. There is an option, instead of force, you have a clock. You can directly give the clock with the duty cycle and the time period 100. By default, you can give that. So D input, I am supposed to give any input. Let me force some value of 1 here. And Q is my output. So you need not give anything. Reset, always make sure whenever you are using reset, to bring it to the known state, first you make it as 0, then 1, then 0. So make sure that is made, so now you have made a reset equal to 0. Now again change this reset to 1. Then you run this. Then again make reset to 0. This is to make sure that the reset is properly enabled. Now look at here. So when the reset is 1, immediately the Q goes to 0. Can you see here the next clock cycle? So though I give here, it gets effective. I think, can you look at this reset? I am giving reset equal to 1, but it is not getting immediately reflected in your output Q. When it get reflected in the next passage of the clock. Then alone it goes to 0. Got my point? Again, I am making reset equal to 0. That get reflected only in the next clock cycle. Got my point? So now let us see. This is my clock period. D equal to 1. So what did I said? When the reset equal to 0, during the passage of the clock, whatever there in D will be passed on to Q. So during this time, passage of the clock, this is 0. So this value comes to 0. This is during this risage of the clock, input D is 1. So the output goes to 1 here. Can you see here? Q. If I make this as 0, let me make this as 0 and see whether that is getting reflected in the next clock cycle. Let's see. Yeah, it is getting reflected in the next clock cycle. Can you see here? The D Q value changes. Are you all following me? You can force 0. Then, yeah, the output goes to 0. Simple. So it works as a perfect D flip-flop. Correct. Now let's see something else. So in that you can try with all type of D flip-flops, all other flip-flops too. And in fact, you can also extend that to modulo counters, decoders, encoders, all those things. For want of time, I am not doing that. Let me see the clock generation circuit. Maybe you could understand this. Look at here. Clock generation circuit, module name, clock, clock gen. I have declared the clock as output, initializing the clock to 0. And inside an always block, I made for every 5 unit of time, you get a new clock. So if you start running this, you will get a clock. So let's try to check this. Go to simulate clock gen. Go to work folder. Clock gen. Sorry. Somewhere here. Yeah, it's here. Check it. Okay. Select this. Add to waveform. Selected signal. So it should appear here. Yes. So let me start executing it. Yeah, simple. So you could see the time period exactly what we have mentioned there. So this is somewhere around this is 48, 49, 50, 51, 52, 53, 54, 55. So the time unit is 5 unit of time, 5 picoseconds. Got it? So the code, what we have written, clock gen for every 5 unit of time. So by default, 5 picosecond. For every 5 picosecond, the clock, I mean, the total time period of the clock is t equal to 10 picosecond. Right? If you want, you can even change this, and you can see that the time period varies. You can generate your clock according to your own requirement. Correct. Now let's move on. Again, up-down counter also it is there. Of course, there is one test bench for that. Maybe we will look into that, and we will also see one more. What does the up-down counter program, where it is? Here it is. Okay, look at this. A simple up-down counter. Maybe I think we need to check using case statement also. We will see. We will see one example with the case statement. Yes. So this is a mere up-down counter. Up-down counter count is 2 down to 0. We have defined parameter. One more thing. Now a same counter, we are going to use that as up counter and down counter. It's actually like it comes under some other project for a different state machine. It's not for this. So based upon that, we have defined count up, count 6, count 1. So based upon that, we have given. But the point here is, so whenever 0 is given, when the parameter 0 is given, it start counting up. Whenever the parameter down is given, it start down. 1 is given, it start counting down. So it keep on counting it up. Let's not get into this program because this is actually a part of one larger module. I think there is one more counter which is specifically meant for that. This up-down counter is for one FSM state machine. But I am interested to show you how the test bench look like. Yes, now look at here. Module, up-down test bench. Now, whatever there in input that has been made as a reg, output has been made as a wire. You can easily notice here. So this clock and reset has been declared as reg. 2 down to 0 count output has been declared as wire here. Can you see here? Then we called this module, up-down module, So up down, U1 is an instantiation name. We had followed the same order and initialize the clock equal to 0. Always remember when it is having a clock, your system has a clock, first initialize that clock to 0. Then only inside an always block you can have a continuous clock pulse. Otherwise, we don't know in which state the clock is. So always initialize clock equal to 0. Then under an always block, you go with having a clock definition. Then another one more initialize block, you are initializing reset equal to 1, 0, then initializing reset equal to 0. This can run up to 4 unit of time period. That's all. So whenever you give 0, whenever you give 1, it start. So reset equal to 0, it start counting up, counting down, and reset equal to 0, it start counting up. No. It is mere based upon the reset, based upon the parameter. I think we have not defined it. So you can go ahead and define based upon your requirement. Whatever input value you want to give, you can give it. Finally, give a dollar finish after what time interval you want to run. Right? That's fine. Let's take one more. I think on that day we have seen that 4-bit adder. So I'm not going on with that. Let's see the case statement. Yes. So still now you have not seen the case. Let's see an example for a case. Look at this. The same mux definition has been done with case. So initially we made an expression. Next we made an assign statement that is in data flow style. Then one with structural style. Then now we will see in behavioral style. Look at here, mux case, A, B, S, Y. We have defined all this input output. Now simply I am using always block just for defining the combo logic. So A, B, S. Got it? Now let's see. Inside an always block only, you can have if, else, and case that you need to remember. So case yes means for this yes, if you have 1 bit 0, then assign y equal to A. If it select line is 1, you assign y equal to B. Default, assign y equal to high impedance. If nothing is there, 1 bit high impedance, sorry. If default, if nothing is there, say something like this. Sometime what happened, why should we give default here? Of course, in this case, default doesn't matters a lot because there are only 2 options. So you will not have any problem. I am using 2-bit select line. Okay. Now I have defined for 3 cases like 0, 0, you are supposed to do this. 0, 1, you are supposed to do this. 1, 0, you are supposed to do this. I don't have any other cases. I have only 3 cases. So using this case statement, I have defined for case 1, case 2, case 3. Now I have not explicitly defined what should I do if the select line comes 1, 1, because there is a possibility. Though I am giving instruction only for these 3 cases. Okay, I am giving a set of instruction. For the 4th case, I don't have any option. I am just leaving as it is, and I write the code it as end case. If I do so, then it will create a latch at the backend during synthesis. Why it is so? Because you have left something where those unprescribed condition will end up with a latch to store that value. So you need to say here explicitly, right? When 1, 1 comes, what it need to do? If not, you need to define a default. For all other combination of your select line, you follow this. That is the reason it has been shown here, that you could see here. Sorry. Default for all other value of select line, because select line cannot take more than this. Oh, of course, it can also, because 4 values, it can take X and Z also. Under that case, you need to give a high impedance as your output. This is what we are trying to say. In fact, you can even check. Give the select line as X and try to run this. You will get Z to be your output in case. Right? So, mostly people make mistake in the case, in case, and this colon. Colon is very important. Here it is a single line, so I didn't start with begin and end. If that is there, then you can, more than one line is there, you can define begin and end there. And sometimes you can also use if inside an case also. Got it? So inside this one tick binary or any case option, you can define a if statement inside that also. Right. Yes, the major part is over. Now I am going to touch one more important topic. What do you call it as FSM? With that, I think we can wind it up. Let's see what is that FSM, how it is important. Yes. Right. This FSM is one of the important topic where most of the time we write a code in FSM, say finite state machine, particularly for all real-time problems. Say something like a lift, right? While you want to write a code. So while my lift is in the second floor and someone press in the fourth floor, where should I go? Simultaneously, there is one person pressing down in my first floor. Should I need to go first there or come over here? Or simultaneously there is a call in the 8th floor. So at each and every state, if I am staying at some particular state, what should I do? What should I give as my input? This is what you are defining. One more example. Let me do one thing. You would have gone for the ticket vending machine. Ticket vending machine, TVM. Railway ticket vending machine. So let me assume that the ticket cost is 10 rupees. Got it? Now, you look at the machine. If you give 10 rupees, it will give a ticket and nothing as a balance. In case if I am giving 5 rupees, it won't give a ticket. Under that case, it waits for another 5 rupees. So 5 plus 5. Now, it gives a ticket and no balance, zero balance. Let me give 20 rupees, passing it on. So it gives me a ticket and one more 10 rupees back. Now I'm just defining, see how many possibilities. Just for getting a ticket, I want the machine to be intelligent and getting all this cost. Sometimes some people will give 2 rupees, 2 rupees, 2 rupees. So for every 2 rupees, it goes to a new state, right? And finally, it has got this 10 rupee and it issue a one ticket. Sometimes people used to make like this, 5 rupees plus 2 rupees plus 2 rupees plus 2 rupees. Now under this case, it is expected to give 1 rupee balance and one ticket. So all this practical problem, real-time problem, will always be an FSM based. So you need to know how to make an FSM, finite state machine. Here the main concept is, if I am staying at a particular state, if my input comes, do I need to go to which state, to which state I need to go. Second, what output should I provide? If you answer for these two, that becomes an FSM. Got it? So every state you can stay based upon the input which you receive, you make the next to move or next to move to the state, other state by delivering certain outputs, right? Okay. So what are the types of FSM, finite state machines? There are two finite state machines. One is Mealy machine and Moore's machine. Of course, you all might be aware of, right? The simple idea in Mealy machine is the output depends upon present state and the input. Simple. Whereas Moore's machine, output depends upon only the present state. Okay, present state that you could see here. So this is my present state. The output depends upon only this one. Whereas look at this Mealy machine, present state plus the previous value has also been fed over here. Got it? So the output depends upon the previous input as well as the present input. So always it is like this. When you look at the Moore's machine, the state diagram will be like this. So this is state A, this is state B. The output is being given in the state, present state. It may be 0 or it may be 1. Only the input is being mentioned in the state transition diagram. When you come to Mealy machine, this is state A, let this be the state A, let this be the state B. If I am moving from A to B, the output is being given during the transition input, like one input, the output is also being given during the transition. So here the output is given in the state, means the output depends upon the present state. Here the output depends upon the present state as well as input, you get the output. Generally, the Mealy machine require n number of states, whereas Moore's machine require n plus 1 number of states. So generally people will prefer Mealy machine for the simple reason you have one number of state lesser than that, no? So naturally you have less resource requirement compared to that of Moore's machine. Is the point clear? That's it. So you could see here very simply. So the Mealy machine, the next state and the output depends upon the present state and the input. Okay. So you should always answer for two questions. What would be the next state from the current state? What would be the output? So here the output and the next state also depends upon present state plus input. Got it? Right? Whereas coming to Moore's machine, the next state depends upon the present state and the input, whereas the output depends upon the present state. Output depends upon the present state. Next state depends upon the present state and the input. So that's the main idea. Got it clear? Right. Yes. Now I think it is better to go with this FSM by taking one example and writing a code for that. Generally, most prevalent one example is the sequence detector. Let's take the sequence detector. What is a sequence detector? Very simple. It is nothing but an FSM. Of course, you can define this FSM as a Mealy machine or Moore's machine, that's left to you. But what it is going to do? A series of input can be given and you are looking for a pattern. If that particular pattern comes, then it will give 1. Say suppose I am looking for a pattern 1010. So one by one while you feed the input, it always look for, oh, first one came, next 0 comes, next 1 comes, next 0 comes. Oh, required pattern is reached. It will give your output at this point. And for all the remaining thing, it will not give your output because that is not the required pattern which you are looking for. Got my point? So simple. Yes. See, let me give still one more example. I am having like this. This is my series of input. I am asking the machine to find out if there exists a pattern 101 that comes in, right? So it just goes and look for, so first 101, okay, it will give 1 at this point, and the remaining thing will be 0. Again, you keep on looking here, nowhere. This is also 0, okay? So nowhere, then it gives 1 here. All the remaining things are 0. So I need to come up with a circuit which will look for a sequence of pattern in the given input, and whenever that pattern arises, it need to give me 1, else it need to give me 0. That's my idea. Can you give us an example where the sequence detectors are used? Yes, many places, particularly in digital data transmission and pattern generation, pattern detection, you have a huge requirement for this. Of course, this is a very rude example, but many places where you want to synchronize your data, looking for some pattern, not pattern here, though you take it as a 101 pattern, it could be some control signal. You could take it in this way. If someone press, that is going to create a pattern of 101 in your control signal. So that might come as an input. So I might be continuously watching for that, right? So rather than considering this as a pattern, you could consider that some control signal which is generating a digital pattern. You could also consider like that. Right. Okay. Now let's give some example with state. Yes, that's what we are going to do now. Okay. Finite state missions we have seen here, and we will go with this one example. One more thing, there is something called as overlapping, non-overlapping. But mostly we go with overlapping, but for classification sake, we will look for non-overlapping also. Say for example, this is my input. If I am looking for a pattern 1101, then I will keenly watch this. Up to this point, you will get 1 here. And after that, this won't be the pattern which I am looking for, 1101. Had if I could consider this also, the last bit, and see, it could give me 1101, right? Got my point? 110, 110, 1101. If it is non-overlapping, I will be getting, I am looking for actually 1101 pattern. Non-overlapping, here you will get 1. And definitely this you will not get. One more 1101, I will get 1 more here. This is for non-overlapping. If I am looking for overlapping, what overlapping means, the last bit can be the bit pattern for the next, right? Subsequent sequence. So you can have this 1101, and the last one can also be a pattern for the next one. 1101. So you will also get 1 more here. And of course, this is again being a part of the next one, 1101. So it is 1 more. So generally, it is always good to have a overlapping sequence rather than going for a non-overlapping, because non-overlapping gives output less. Okay, that's it. That's what you mean by overlapping, non-overlapping. Right. Now we are entering into a problem. Now the task is, now we are going to come up with an FSM, design the FSM, write the code, and test it for this sequence. Say for example, let's do here. I have been asked to come up with an FSM design for detecting the value 101. Right? So what am I supposed to do? Let me first start with a single state. In this, if reset is there, if reset equal to 1, it is supposed to come to this state. Okay, time being, let me keep that first state as S0. And remember, to detect this 101, I can go with Mealy or Moose. Right? Now, let us discuss the Mealy method of design and coding. Of course, you can also extend the same thing for the Moose also. Right? So, if at all reset is given, I am starting with the initial state. This is I0. Next, not only that, if input is 0, then what will happen? The output is going to be 0. This is a Mealy machine, so I need to, this is the present state. If input, always remember in the transition diagram, input versus output. That is the transition diagram. So input is 0 because that is not my desired output. Desired pattern which I am looking for. I am looking for 101. So if 0 comes, I need to be in the single initial state only. So I without giving any output. So it will still stay at S0. Say I am giving input equal to 1. What would happen? So it means that the first bit of your required pattern is being acquired. So you go to a state S1. Should I give any output? No, because I have received only the first input of my pattern. Next, what if after coming here, you have reached this state? Now, after coming here, the expected value is 0, right? But if I get 1, then what should I do? It is like getting two patterns, 1, 1. For me, it is same as the first one only, because now this one becomes useless because I am looking for 101. So it will still be at the same first state by providing output equal to 0. If it is in S1, S1 means what? In this state, it has received the first one. If it received 0 as your input, then it will go to the state 2 because the second bit is being received by it. Then what is your output? Output is going to be 0. Why 0? Because it is there in, it has received only the second bit. Got it? Next. What if it is already here? What if it is receiving the third one? Now, 1, it came here. 0, it came to the second state. Third, one more, if it reads 1, now it has got the required pattern, 101. So it is expected to give 1 as my output. But what should be the next state? If it is non-overlapping, it would go here. If it is overlapping, this should go to the S1 state. Why? Because it is equivalent to the first bit being received. If not, after receiving 1, 0, it is again receiving 0. It is useless. Again, you are starting from the same point. Is this FSM clear? If this is clear, then there is nothing difficult in writing a code for it. Simple Mealy machine diagram. If you want, I can repeat once more. How many of you clear? You can just type clear, repeat. Let me see. Few more answers so that I can decide whether to repeat this or move about. Clear. Clear. Not clear. Okay. Repeat. Let me do that once again. Let me start here. So this is the pattern which I would like to obtain. So what I'm trying to do. So first, what is my idea? It is like this. Let this be the circuit. This is my input. Now, it has a series of pattern 1 0 1 1 1 0, something like this. A pattern is coming up one by one bit. I'm supposed to keenly scan this, and whenever I obtain this 101, I need to give here, hey, I have got the required pattern. If not, I will be giving 0. So for that, I am trying to design a circuit. The first job, first to make an FSM. FSM, it is going to go through different state. Why different state? The reason is I am getting 1 by 1 bit for every. It is something like the coin said, no, for 10 rupees railway ticket, I am supposed to get 1 rupee, 2 rupee, 5 rupee, like this. I keep on getting 1 by 1. I reach that 10 rupee. The same thing scenario here, 101. So first state, it is an initial state. So whenever people give reset, it is expected to be here. Let me keep this state as S0. If some people give input as 0, so the output is going to be 0 and it is going to stay at the same state. Now, if some people give 1, right? If 1 is there, it is expected, the expected pattern, first value is reached. So it go to the new state. It is something like out of 10 rupee, it has reached 2 rupee, right? So it is entering into the state 1. But does it produce any output? No, it doesn't produce any output. Output is 0. It is something like only if I get 10 rupee, I am expected to give my ticket. Otherwise, everyone will get the ticket even if I put 2 rupee and they will move out. So the output is 0 here. Next. Now you have in the state, which means you are staying at by receiving the first one. Now the chances are there, you will get input as 0 or 1. If it is 0, then you are getting the second input. So if it is 0, you are not going to give any output, but you are going to the state S2, which means at this point, you have received 1 0. Still, you have not received 101. Got it? Right. Now, if you get 0, you go here. In case if you get 1, what is going to happen? You are getting 2 subsequent 1. 2 subsequent 1 is same as having, say, like this. Now, even if you get this one, you are still looking for this position only. It is same as getting the first one and looking for next 0 1 only. So if at all, if you are getting 1, I don't give any output and still I will be staying here. So every state you just look for, if 0, if you get 0, what should you do? If 1, if you are getting, what should you do? Got it? Next, finish. Now from this point, again, let's see. In S2 state, if I get 0, it is something like 1 0, because already this is in 1 0. If you are getting 1 more 0, it is typically going there without producing any output. What if I am getting 101? Oh, that is my required pattern. So in case if I am getting 1, in case if I am getting 1, then I am expected to give the output because 101 is reached. That is okay. But where should I go? Again, you go and wait here. Why? Because next pattern may be something like this. This 101 is one pattern. This is overlapping pattern. No, again, this last bit can be the first one for the next set of pattern 101. That's all. Nothing else. Simple. Once you make this, then all the other things, writing a code is damn simple. Nothing else you need to do. That's it. Okay. Right. So you have made that. So how many bit? I mean, how many states are there? 3 states. You code each state. So for 3 states, I require minimum 2 bit. 0 0, 0 1, 1 0. This is what I said. Some default condition you need to represent default. What is what? Okay. Sometimes there are the latest tools are a little bit intelligent enough. Even if you don't define that, it will take it. Okay. So now look at here. So for every state, I am assigning the state a particular binary value. Why it is so? To represent each and every state, I require flip-flop. So maximum 3 state, I can represent the 3 state by using 2 digit or 2 flip-flops. So that's 0 0 0 1 1 0. Those are the things. That's it. Now the design part is over. The same thing when it comes to Moore's machine, the concept is simple, same idea, except the number of state will be one more, n plus 1. So there it is 3, now it is going to be 4. Point is clear? Right. Now let's see what I'm going to do. The same 101 pattern. Now remember, in the transition, you are going to represent only the input. The output is represented in the state itself. In the state itself, you will get the output. So let's start from the first. It is in the initial state, right? If reset is there, then it is going to come up with the state 0. One more thing, if people give 0, then also it is going to stay in the same state by giving the output as 0. What if the input is 1? So if input is 1, it has entered in the first one. When it has got the first one, so it moved to the state S1. It will not provide any output. The reason is, in the S1 state, it has received only 1 out of the expected 101. Right? So now it is in this state, which means in this state you have already received 1. After this, if you get 0, then what it need to do? If you get 0, it go to the state S2. There also it will not provide any output. Why? At this point it has received only 1 0 in this state, right? So if it gets 0, it goes here. What if it receives 1? If it receives 1, it is supposed to stay at the same state. It is something like getting 1 1. Got my point? Now, okay. So coming here, now in the S2 state, it has already received 1 0. Now you need to answer for what if 1 comes, what if 0 comes. If 1 comes, 1 as an input, then it goes to S3 state, which means here it has received 101, which is the required pattern. So it need to give your output. What if 0 comes? Instead of 1, you are getting 1 0 0. Then it need to go and start from the very beginning. Right? 1 0 0 means you have lost 1 0 0. It is again starting from the beginning. So if you are getting 0, it will go here. Okay, now you landed up here. 101. Next, what should happen if I get 1 or 0? If I get 1, it is something like 1 0 1 1, which means it is something like getting the 1 for the next pattern. So if I get 1, it will go to the S1 state, which means it has received like this. If I get 0, instead of this, if I get 0, I can consider this as a overlapping pattern for the next one, 1 0. So it can go to 1 0 pattern if I get 0. Simple. Are you following me? For how many of you this particular state diagram is understood? Super. Clear. Yes, that's it. Very simple. Once you understand this, there is nothing in the coding. Now we will go to the coding. That's it. For the same example, I have written the coding in Mealy Machine. Yes. Now look at this code. .p file. Right. So now it could be easy for you to understand. Look at this. Right. Well, generic thing is, yes, you go with module, you define all your input. Input is basically IN is going to be your input, that is input pattern. Beyond that, you have a clock and reset since all these are sequential network. Then output is a single bit. So I am defining input, clock, reset, input. All these are single bit. So I have mentioned like this. Output reg is your output. Now look at here. In the FSM, which we have made, right? What we could see, there are 3 states. So for every state, I represent by 2 bit. So I use parameters. Parameters is nothing but instead of giving S0, S1, S2, I am representing that by 2 bit. That's why I have represented this as a parameter. S0 means 00 bit. S1 means 101. Like these 3 parameter statements are used to represent the state in binary. This is what you call it as a state encoding. Then one more thing I am adding up here, just as a temporary thing. What do you call it as a current state and next state? This current state is the state at which it is available. Next state means when it gets some input, to which state it is moving on. So I am defining 2 states. These are very generic template, right? So when it is in one state, it is getting an input to which state it moves on. So 2 states I am defining. One is current state and the next state. Then all the other things are simple. Go with an always block, passage of the clock. If reset equal to 0, simply make all the thing as 0. That's what we have done. Output 0, current state is 0, next state is 0, everything is 0. Make sure they are within the begin and the end because there is a series of statements. Okay, reset is not 0. Here comes the real problem. This is what we are going to define. If reset not equal to 1, then what else? Begin. Current state equal to next state. So whatever the state is going to be there, that becomes the next state. Now I am using a case statement. So the current state is something like this. I am simply defining this current state. If the current state is S0, so go to the diagram. Current state is S0. What is going to happen? If current state is S0, if the input is 0, output is going to be 0. And the next state is also S0. That's what we are mentioning here. Look at here. Output equal to 1 bit binary 0. Next state is, if the input is going to be 1. If here input is going to be 1, next state is 1. That's what it means. Next state, NST refers to next state, S1. If it is not 1, if input is not 1, then else condition here. Output is going to be 0, the next state is going to be S0. Are you following here? I am taking the state. Look at here. I am defining 2 cases. What if in S0, if the input is 1, it goes to S1 and the output is 0. That's what we have mentioned here. What is the next state? What is the output? Else, here input is not equal to 1. What is the next state? What is the next state is going to be S0, output is going to be 0. Got my point? Like this, you need to define for S1 and S2. That's what we have defined here. Look at this. In S1, let's assume. If input is 1, the next state is S1, output is going to be 0. Input is 1, output is going to be 0, and the next state is going to be S1. If the input is 0, it is going to the X2 state, S2 state, and the output is going to be 0. Simple. That's what we defined in S1 state. Coming to S2 state, same story. Input is 0, output is 0, and it will be going to the state S0. If input is 1, it is going to the state S1 by giving the output as 1. That's what you could see. Output is 1, going to the next state as 1. Else it will be going to the first state S0. That's what So you have defined all the three cases, case CST, S0, S1, S2, end case, then end begin, and finally end the module. That's all. Very simple program. So the general template is two things. Define the parameter, define the current state and the next state, construct one always block. Inside an always block, if reset equal to 0, make sure that everything goes to 0. Else you simply create one case statement. There you give the answer for what will be the next state, what will be the output in each and every state. Once you do that, that's all. The whole program works. Let's write the test bench for the same. Now coming to the test bench. Simple. The same thing is being narrated here. Look at this. A module is being created with the Mealy FSM 101 test bench. All the input has been made as a range, output has been made as a wire. We called that module with the same port list. I am initializing everything with the clock, reset, input, everything as 0. Then look at here, whenever reset comes, make it as 1 and then make it as 0. That's what we have done after every 10 interval of time. After this, I am giving series of input. See, input 1. After 10 unit of time, input 0. After 10 unit of time, I am giving input. These things are delay, so that sufficient time is being given for the next input. After 10 unit of time delay, I have given 1. So I have given pattern 101. Once this pattern is reached, it is expected to give me the value of 1. Now look at this. You are ending this. Inside this initial begin, you are ending this. And I am supposed to generate a clock. So I put that inside an always block. #5. All the delay I have given it as 10. But the time period for the clock is definitely less than that. This you need to make sure. Otherwise, you might not get a proper result for the simple reason it might fail to sample that value. So #5 clock equal to inversion of clock n module. That's all. Any doubt in these two programs? Clear. Okay. So now let's try to run this program. Go here, simulate, start simulation. Let me go with the Mealy Machine. Mealy FSM 101 test bench. Fine. Right, fine. So I am collecting all the input. Copy that to the waveform. Selected signal. Yes. Now let me simulate this. Now let's try to analyze here. Look at this. So this is my clock. Then once I make the reset equal to 1, the output goes to 0. Now you look at the input pattern. Here it is 1, 0, 1. When once it received 101, the next clock cycle it is giving me the output as 1 because it has received that pattern. Can you see here? 1, 0, 1. After receiving that, in the next clock cycle, it is giving me the output is given as 1, which means that it has received the pattern 101. Pakka. So it's working perfectly for this pattern detection 101. The same thing could also be extended for Moore's machine. Only thing you need to make change the code, two things. Exactly the code will be the same except 2 points. Instead of 3 state, you will have 4 state. One more. And in the definition of output, here you have defined the output after receiving the input, because Mealy machine gives their output after getting this input. But in Moore's machine, you should not give your output here. You comment here. Oh, I forget to say this. Double slash is a single line comment. Slash star and till the end star slash. It is the whole bunch of code being commented. You can do like this. So you comment this and give it exactly here, because this output depends only on the state. Only these two changes you need to make. So extra one state, bring the output out of the if input block, and the output should depend only on the current state. So inside this if else block, you define what should be the next state. That alone. That's it. You are ready with your code for Mealy machine, Moore's machine. Probably you can do that as an exercise and go ahead. I believe I have done everything. So if you have any doubt, post it here. As far as the point of coverage is concerned, we are completely done with 1 minute. So I think we are having one more. By next week, we are having one more session, which completely speaks about VLSI, which means